Howdy y'all. In this video we're going to introduce propositional logic or sentential logic and talk a little bit about this sort of symbolic language and its logical connectives, how to translate English sentences into this symbolic language, and a little bit about the calculation of the truth values of the sentences created in this language. So to start with, we're going to talk about just what the logic is sort of made of, so sentence letters and logical connectives. So propositional logic is a branch of logic that looks at the process of connecting or modifying existing sentences with logical operators. And this is something we've seen a little bit already in chapter 3, where the patterns of arguments that we looked at involved conditionals and negations and disjunctions, where you're taking sentences and making new sentences with these logical operations. Now, what we're going to talk about from here on out is sort of a symbolic language, and we express these things sort of symbolically because that's going to make things a bit easier when it comes to calculating the values of these sentences. So the sentences can be very complex, and the symbolic nature makes it easier to talk about these things. All right, so the language that we're going to talk about has sort of two elements. So the first element are what we call sort of the sentence letters or atomic sentences or simple sentences, which usually get a letter of P, Q, R, or etc. And these are just stand-ins for sentences, and they're stand-ins for sentences that have truth value. So you take an existing sentence, you call it P, and then from that you can modify that sentence with a logical operator or a logical connective. And in the language that we're going to discuss, we're going to talk about sort of 4 different logical connectives. The conditional, which is expressed symbolically with an arrow, the disjunction, which is expressed with a V here, the conjunction, with this, which we use the and symbol, and then the negation, which gets the tilde. So all of these are going to be ways in which we can sort of construct new sentences by modifying existing sentences. So it's important to remember that these sentence letters then we're going to stand in for any sentence that has truth value, which is either true or false. So we're talking about claims or propositions here. So they have a truth value, and that's going to be important to our discussion. And then as we said, the logical connectives. So I just want to go briefly through all 4 of these just to show you how they work. So we have 3 of our connectives we call binary connectives, and what they do is they take 2 things and put them together. They take 2 sentences and put them together and creates a new sentence. So conditionals, conjunctions, disjunctions are all binary connectives. So they take a P or Q or whatever, they take the sentence and put it together. So you get, with conditionals, you'll get P arrow Q, which in English is if then, so if P then Q. Conjunctions are and sentences, so you take 2 sentences together and you make P and Q. Disjunctions are or sentences, P or Q. And then negations are not binary, so negations modify just one sentence. So you take any sentence that has truth value and you can negate it. So tilde P just means not P, so it's not the case that whatever P is. So here's an example here. So we've already in chapter 3 discussed sort of modus tollens. We said, look, this is an argument pattern that is valid, and so here's an example of something that kind of fits the pattern in English. If I live in Milwaukee, then I live in Wisconsin. I don't live in Wisconsin, therefore I don't live in Milwaukee. So what's going on here, and what we talked about sort of in chapter 3, is essentially we have an if-then sentence, if P then Q, or a conditional sentence, what we call it. Then we have another premise, which is a negation, so not Q, and then the conclusion that is a negation. So if we, introduce our symbols here, we're just going to replace that sort of if-then with an arrow, and we're going to replace those nots with a tilde. So we get sort of a more symbolic looking expression here. So P arrow Q is just if P then Q, tilde Q is just not Q, tilde P is just not P. So that's kind of where we're going here with this. All right, so we have the four connectives, and just want to talk about a little bit of translations into those connectives. And especially with conditionals, there's a lot of different ways in which you can sort of utter a conditional that would just get sort of translated as P arrow Q. So very straightforwardly, if I live in Milwaukee, then I live in Wisconsin. If I live in Milwaukee is the P, and I live in Wisconsin is the Q. That's sort of the most straightforward. It's just if, then. But it's also the case that P only if Q, or I live in Milwaukee only if I live in Wisconsin, also gets translated as P arrow Q. So even though the if kind of moves around from being in front of the P to in front of the Q, the only if comes in front of a consequence. So same sentence here. In fact, all of these are the same sentences. All of these would get translated as P arrow Q. So living in Milwaukee is a sufficient condition for living in Wisconsin would be P arrow Q. Living in Wisconsin is a necessary condition for living in Milwaukee, would also get translated as P arrow Q. Bear in mind that with conditionals, right, the antecedent is always the sufficient condition, where the consequent is the necessary condition. So the order that you put these things in matters. So conditional is going to be kind of tricky. There's lots of different ways to utter a conditional. Disjunctions have sort of fewer options, but there's sort of a couple different ways in which you can do sort of disjunctions. So disjunctions are typically sort of or sentences. So you could say like either I live in Wisconsin or I live in Illinois. So if I live in Wisconsin is P, I live in Illinois is Q. You get PVQ, but I think most people will recognize a disjunction even if you drop the either. So you could just say I live in Wisconsin or I live in Illinois. It'd be the same translation. But one thing that is kind of different is the phrase unless. So we do use the word unless to indicate disjunctions, and so I live in Wisconsin unless I live in Illinois also gets sort of translated as PVQ. So just something to sort of keep in mind, that unless it could be a tricky one. Unless is a disjunction. Conjunctions also have sort of a couple different sort of versions. So and is the most common. So I live in Madison and I live in Wisconsin is a conjunction. But the word but is also a conjunction. So I live in Madison, but I live in Wisconsin. It has a slightly different meaning than and, but from a logical point of view, it has the same logical function in terms of truth value. So what makes an and sentence true is the same thing that's going to make a but sentence true. So just something to keep in mind. And remember, these are all the binary connectives, right? They all take two things together and put them together with this connective and makes a new sentence. So there's the one unary connective, which is negation. A number of different ways to sort of negate a sentence, but here's two of the most common. So if you have the sentence, I live in Milwaukee, think of ways to sort of say the opposite. I don't live in Milwaukee. It's not the case that I live in Milwaukee. Those are the most common ways to sort of negate an existing sentence. So in this case, uh, we're mentioning two. Okay, time to move on. So from these sort of simple sentences and these simple sort of connections where you take a simple sentence and make a complex sentence, it's important to sort of note is that you can keep on going and construct more complex sentence. So bear in mind that once a sentence is modified or connected with a logical connective, it becomes a new sentence, and that new sentence has truth value, right? So you can understand that sort of new sentences as being a P, right? Again, sort of P's can be stand-ins for any sentence with truth value. So this new sentence can be modified or connected to another with a logical connective. So this process can go on indefinitely. So because once you modify or connect that sentence, it becomes a new sentence, and that in turn can be modified or connected, and so on ad infinitum. So an infinite number of sentences are possible in this language. So when we start constructing complex sentences, we introduce parentheses to the language, which are used to help sort of demark sentence boundaries, which help us kind of make sense of what's being negated and what's being connected. And the only sort of exception here is with atomic sentences. So if you're just negating a sentence letter, then you don't need to sort of add parentheses. It's sort of understood that a negation right next to a letter only sort of covers that letter. It doesn't cover, its scope isn't sort of any broader. So that'll be a little bit more clear when you sort of see examples, but just to put that out there right now. So here's an example of constructing a complex sentence. So suppose we'll just start with a sentence, P, and one thing we can do is add another sentence to it. So we'll add Q to that sentence. So now that's a new sentence. So we can do things to that new sentence. We can modify or add. And in this case, we'll modify, right? So let's take that sentence and we'll negate it. So we have not the case that P and Q, right? So it's not the case that both P and Q. Take any two sentences, put them together, you can negate both of those because it essentially means that either not P or not Q, but not both is a fairly common expression. But you can modify that further. So let's add R to that with a conditional. So we'll say if R, then not both, right? Then if R, whatever R is, then it's not the case that both P and Q. So that's a fairly complex sentence, but but it is something that you can express in English. It's just easier to see the structure in its symbolic form. But in English, you could have something like this. If I go to the store, then I will not both watch a movie and go to the bar, right? So maybe I only have time for one of those things. So if I go to the store, I won't do both, right? I won't both watch a movie and go to a bar. So that's that's an English sentence, and it has truth value. And not R, arrow, not the case that P and Q is what it would look like. All right, here's another example. Again, just starting simple with a P. We'll add Q to it. In this case, we'll use or instead of and. So it's a disjunction, P or Q. And we'll take that and add a negated sentence, so with a conditional. So we'll say excuse me, if P or Q, then not R. And so that's a sentence. And in English, it might look like something like this. So here is my sports sentence that I say that if either the Bears make the playoffs or the Vikings make the playoffs, then the Packers will not make the playoffs, right? So the P here is Bears make the playoffs. The Q here is Vikings make the playoffs, and the R, not the not R, but the R is the Packers will make the playoffs. So not R would be Packers will not make the playoffs. So that's why we got that negation there. So again, a fairly complicated sentence, but if you look at it in the symbolic language, you can see its structure a little bit more clearly. All right, so the next thing that we need to talk about is how to calculate the truth value of these modified sentences or these connected sentences. So as we mentioned, the letters, the individual atomic sentences have truth value, and that the complicated sentences also have truth value, but we need to know how to figure that truth value out. The truth value of the simple sentences will be very simple. They'll either be sort of true or false. But how do we figure out the truth value of the more complicated sentence? So one thing to say is that the truth value of the complicated sentence depends on the truth value of each sentence letter, of each atomic sentence. So if your sentence has a P and a Q in it, then whether or not that new sentence is true is going to depend on the value of P and the value of Q, and it's also going to depend on the logical connective that is involved in the creation of that sentence. So by analogy, think about algebra. An algebraic equation depends on the value of each variable in that equation and the mathematical operations involved. So here's an example. So let's compare the value of this logical expression. So on the left here we have a P and not Q, which is a sentence that we've connected to R with an OR symbol. And then on the right here is an algebraic expression, a fairly simple algebraic expression, x plus y minus z. So for those of you who have some knowledge of algebra, if you are told the value of x, y, and z, you should be able to figure out the value of the whole expression, right? And that's because, well, first, you're given all the values that you need, and secondly, you know what the mathematical operations do, right? You know how simple arithmetic works, right? So if I tell you that in this case of x plus y minus z, if I tell you that x is -1 and y is 3 and z is 5, then you know how, or at least most of you would know how to kind of figure that out. You know that you work within the parentheses first and do the addition, right? So -1 plus 3 is 2, and then now you subtract 5 from it, so 2 minus 5 is -3. So you know that the value of the whole thing is -3. So what we want to do is be able to do something similar with our logical expressions. So the difference is going to be, though, is that that our variables, right, our p's and q's and r's, only have two values. That it's either going to be sort of true or false. So if I tell you that the value of p is true and the value of q is true and the value of r is false, you should be able to figure out what the value of the entire thing is once you learn how the logical operations work. That you need to know how negation works. You need to know not how conjunction works, and you need to know not how disjunction works in order to solve or calculate the value of this expression. And in this case, the value is false. That's just like looking at sort of a mathematics expression, you should be able to get to a point where you can look at a logical expression and see fairly quickly what the value is. And in this case, the value is false. Again, there's only two values. So this is what we call a binary system, and with only two values. So lots of things work on sort of a binary system, most notably computers. Uh, so what we're going to do then is move on and talk about how to do this work. So first thing to talk about is the rules for each connective. So when you see a connective, you need to know how to go from the pieces of what you're dealing with to a judgment about the truth value. So each connective has a different rule, and we'll start with the binary. So the binary connectives always put there's always two things to deal with at a time when you actually have to use the rules. So for instance, sort of conjunction. There's always going to be two conjuncts, right? There's going to be the P and a Q, or a something and a something else. But anyway, there'll be sort of two values that you have to sort of look at. And the way that the rule works for conjunction is that conjunctions, these and sentences, are usually false. That ands are, just the meaning of the word and is such that unless both of them are true, both of the conjuncts are true, um, the whole thing is going to turn out to be false. So if I say today is sunny and it's windy outside, well, it better be the case that both of those things are happening, right? Better be that both P is true, that it's sunny, or and Q is true, that it's windy, right? So the word and entails that both of those things need to be true. So the rule is then that they're false unless they're both true. Now disjunction, on the other hand, is usually true, right? If I say it's sunny or it's windy outside, I don't intend necessarily, at least, that both of those are true, right? They may both be true. But with a disjunction, all you needed to have is at least one be true. And so the rule for disjunction is different. The rule for disjunction is that they're usually true, unless, of course, they both turn out to be false. So if you end up with sort of false or false, right? So it's not sunny and it's not windy outside, then a disjunction would fail. So usually disjunctions are true, except in that one condition. Similarly with conjunctions, usually they're false, except in that one condition. So all the binaries kind of work this way. There's always sort of one condition that's sort of different from the others. The conditional, the if-thens, they're the kind of the trickier ones, because it's a little bit weirder kind of a sentence. There's a bit of asymmetry with the conditional, because when you say sort of if-then, you're not saying that the first thing is true. What you're saying is what would happen if the first thing were true, right? So it's that hypothetical way of thinking. So if I say, if the sun explodes, then class will be canceled, that's a true sentence, right? That's a true sentence, even though the sun may not explode, right? At least not in our lifetimes. But it's nevertheless true that if the sun exploded, we wouldn't have class. So what we need to say about the rule for conditional is there's really just sort of one condition in which it's obvious that the conditional is false. And that is the condition where the first part is true, the antecedent is true, and the second part is false, right? So if we come across a situation where the first part happens, and the first part is supposed to be a sufficient condition for the second part, and the second part doesn't happen, well, then it's clearly not a sufficient condition, right? Something else must need to happen in order to bring about that other situation. Similarly, if the second part doesn't happen, and you're saying that the second part is a necessary part for the first part, and the first part does happen, then it's clearly not a necessary condition. So again, the only situation in which we kind of care about conditionals being false is where you have true arrow false. So every other situation, like false arrow false and false arrow true and true arrow true, they're going to turn out to be true. So that's the rule. It's usually true, unless that one condition. So all the binaries are like this. And then, of course, there's our negation. So negation doesn't work on two sentences. It only sort of works on one sentence at a time. But it's pretty straightforward. If you negate something true, you get a false thing. If you negate something false, you get a true thing. So as I speak, it's sunny outside, which is true. So if I say it's not sunny outside, I've said something false. And as I speak, uh, it's not windy, so it's windy outside is false. But it's not windy is true. So I've said something true by saying it's not windy because it's the negation of it is windy. Uh, so before moving on to the other thing that we need to think about, which is the order of operations, I want to bring up this chart. So this is or table. This is what's called a truth table. And a truth table just kind of spells out all the possible combinations of the two values of the sentences that you're dealing with. So when you have sort of two sentence letters, and that's kind of what we're dealing with here with P's and Q's, there are actually only four possible combinations of true and false. So on the left in this table, in the little black box, you see those are just all the possible combinations. So in the first row, you have they're both true. The second and third row, you have one is true and the other is false. So maybe P is true and Q is false, or P is false and Q is true. And then you have the fourth and final possibility, which is that they're both false. So these are exhaustive, right? These are all the possible combinations that you could have. And what I've done here, and what we're going to see more of as we sort of go along, is I've just kind of filled out the value of these sentences in each of the four possible combinations. So I have a sentence that refers to each connective here. So we have a P and Q, we've got a P or Q, P arrow Q, and not P. So, and if you fill out this chart, it's just filling it out using this rule. So if you look on with and, the only time it's true is at the top, right? Is when you have true and true. Otherwise, it's false, right? Every other scenario, it's false. So that's just how and works. It's only true under one type of condition. Similarly with or, you'll see that it's usually true, right? Except for that one condition which happens at the bottom where they're both false. Then the same with conditional, right? It's usually true, except for line 2 where you end up with true arrow false. And then the same with negation is if you negate a true thing, which is what's happening in lines 1 and 2, you'll end up with a false thing, and that if you negate a false thing, which is what's happening in lines 3 and 4, you'll end up with a true thing. So that's just kind of the rules in action in table form, and that's going to come up here in the next video about how to fill out sort of truth tables. And so I just wanted to show that to you now. Okay, but in terms of calculating the truth value of sentences, there's one other thing you need to know about, and that's the order of operations. And for logical sentences, it's pretty straightforward. There's just two rules. First of all is if there are parentheses in your sentence, and with the complicated ones there will be, but if there are parentheses, you always work within the parentheses first, right? You need to get rid of all your parentheses as soon as possible, and if there are sort of multiple embedded parentheses, then you work from the innermost to the outermost. So very, very much like algebra, that you do that first. So once you sort of discharge that, then the other thing that you need to think about is a choice between sort of a binary connective and a negation. So sometimes you won't have any parentheses, but you'll have a binary connective and you'll have a negation, or you'll be within a parentheses where you have a choice between a binary connective and a negation. And the rule is that negations go first. That a negated letter is really just it's sort of understood that it would have had parentheses around it, but we took it out just to have fewer parentheses in our sentence. So when you're sort of faced with a negated letter, um, just it's okay to just sort of go ahead and do that first, and then move on. So I'll show you how this works with our examples here in a second. But when faced with a choice um, with no parentheses, but a negation and a binary, you do the negation first. Okay, so the easiest way to kind of to talk about these things is to do some examples of calculating a complicated sentence, but doing it in a way that follows the rules and the orders of operation. So we've got our four rules for each of the logical operations. We've got our two rules for the order of operations. We should be able to then calculate any sort of infinitely sort of complex uh, sentence in the language. So let's do a few examples. Um, so here's what I was talking about at the end of the last slide, right? A situation where you don't have parentheses to deal with, but you do have this choice between the negation and a binary. So we have the conjunction, which is a binary, and the negation, which is a negation. So the rule is that you got to do the negation first before you do the binary. But before we get to that, let's pick some values here. So let's say that P is true and Q is false. So we need to know the values in order to do the calculations. So we'll just sort of state that this is what the values are going to be. They could be different values, but we're just going to pick one combination. And let's go ahead and just replace the P's and Q's with those values. So we have not the case that true and false. So as I stated, the order of operations says you would do the negation first, right? So the negation rule just works on the letter here, so it's just the not true that you need to think about, and so that will become false. So now you've done your negation, and now you have false and false. So now it's time for the and rule, right? There's no other logical connectives left, so all you can do is use your and rule. And the and rule says that conjunction rule, conjunctions are usually false except when true and true. So if it's not true and true, then it's going to be false. So in this case, it's not true and true, right? It's false and false. So it's not true and true. So the value of the whole thing ends up being false. So you negate the true, get a false, end up with false and false, which is false. Okay, example number 2. Here's a little bit more complicated. Now we have parentheses and a negation, right? So this gets to the most important, or the rule with priority is you always work within parentheses first. So even though there's that negation there, it negates that whole business inside the parentheses. So you got to do that inside the parentheses stuff first. So we'll pick some values here. Let's say that P is false and Q is true. So we end up with not the case that false or true. And our first move then is to do the calculation within the parentheses. So inside the parentheses we have a disjunction. The disjunction rule is that it's usually true unless it's false or false. So it's not false or false. That would be the condition in which it's false. So it's some other thing which is true. So inside the parentheses we have true, but again we still have that negation. So we end up almost there, but we have not true. So we got to discharge that negation and do the negation rule. And so we end up with something that is false. So when P is false and Q is true, the value of this whole thing is false. Here's another example. I'll add another letter here just to make the calculation a little bit more fun. And we have not the case that Q and R. So we have some parentheses, we've got some negations, we have a lot of stuff to sort of work with here. But let's sort of pick some values here. So we'll make P false, Q true, and R false. We'll replace those letters just so we can see what's going on. And order of operations time. So we have some parentheses. So the first thing that we need to do is the work inside the parentheses. So inside the parentheses we have true and false, which again is the conjunction rule. So the conjunction rule says it's usually false unless it's true or true. So it's not true or true. So inside the parentheses is false. So now we have not false, arrow false. The second rule is to do the second order of operation is to do negations first. So not false, arrow false becomes true arrow false, right? So you're negating that letter. And true arrow false is false. The conditional sentence rule says that arrows are true unless, and again, there's just that one condition, unless you have true arrow false. So this is that one condition, true arrow false. So the whole thing turns out to be false. All right, another example. Getting a little bit more complicated here. We've got two sets of parentheses, and we'll pick some values here. So P is true, Q is false, R is false. You replace everything, it looks like this. And when there's two sets of parentheses, it doesn't matter what you do first, but I'm going to do the one on the right first because inside the parentheses I have this issue of there being an arrow and a negation. So I'm going to just go ahead and do that negation inside that parentheses first. So then I have true arrow false and true arrow true. I could probably do those both at the same time. True arrow false is the arrow rule. True arrow true is the arrow rule. The arrow rule is that it's true except when it's true arrow false. So that means in the first parentheses it's going to be false, and the second parentheses is going to be true. So there you go, false and true. So now we're down to the last logical connective, which is a conjunction. The conjunction rule is that it's usually false, except when it's true and true. So it's not true and true, so the whole thing is false. All right, moving on. Example number 5. Should probably do a sentence that turns out to be true here. So here's not the case that P or R, arrow not the case at Q, and we'll pick some values. Again, when there's 3 letters, there's 8 possible combinations. So we're just doing, one of those 8 possible combinations here. So let's make P true, Q false, R true. So you get not the case at true or true, arrow not false. So because we have parentheses, we'll start there. So true or true equals true. So that gives us not true, arrow not false. But here's a situation where we'll do the negations before we do the binary, right? Negations before binaries. So you end up with false, arrow true. And now you can do your arrow rule, which in this case is what we have is false, arrow true. The arrow rule says is that they're usually true except when it's true arrow false. So this is false arrow true, which is not true arrow false, and so this is going to be true. So the whole thing here is true. All right, final example. This will be it for this video, and the next video we'll move on to truth tables. But here's a final sort of somewhat complicated sentence. So not the case that both P and Q. So not both. Which, if you think about it, is just both. But anyway, we'll do the computation with our orders of operations. So let's make P and Q both true. That's a combination we haven't seen yet. So you get not T and T. So the first thing you do is work within that innermost. parentheses, so you get not T. Um, and now you got a negation inside the parentheses, so you do inside the parentheses first. So not T becomes false, and then what you're left with is then not false, because there's two negations here, and so not false is true. So it can get a little bit complicated, but that's what we need to be able to do our method. So in the next video, we're going to talk about the truth table method for determining whether or not an argument that's made up of sentences that we can express in this language, but whether or not an argument is valid or invalid.